My name is Marco Badami, and I'm going to present you an activity that we are carrying out under the framework of Horizon 2020. Is a project called The Planet, which is a work. We are working on the planning operational tools for optimizing energy flows and synergies between energy networks. The content of my presentation will be organized in this way. First of all, I will introduce the Planet project with the objectives, stakeholders, and also the scheme of the system that we want to study. And then I will show you a little bit about the architecture of the decision support system tool. And finally, I will show you an example of a first application of the tool prototype. The Planet project is a 3 years European project, and we are at the second year activity, and we will have one more year in order to complete the activity. There are 11 partners from 7 different countries, and Polytechnic of Turin, where I work, is the coordinator of the activity. The objective of the project is to facilitate the integration of renewables into the electricity grid, and this by means a global coordination of the different networks, in particular electricity grid, natural gas and district heating. And this is done by means of assets, and we have a special focus on the power to gas and power to heat, so storage and conversion technologies. The results that we would like to obtain is, first of all, the tool called the Planet Decision Support System to evaluate different scenarios for the maximization of the use of electricity coming from renewables, but we want also to obtain models that can be also used standalone. And finally, we would like to obtain, and this is very important for us, some recommendation for the standardization bodies and definition of new business models and maybe incentives in order to make faster the transition to a more decarbonized European Union. The problem that we want to tackle is that as we know, the photovoltaic and wind power is very volatile, and so we have some problems generated on the electric grid, such as reverse power flow, overloading and power quality. And so sector coupling is well understood that could be a solution, and our tool is a sort of help in order to find out the best way to increase the flexibility of the system. Here you have a scheme, a very synthetic scheme of the energy system that we want to study, which is composed of electric grid, natural gas and district heating when it is available, obviously. And also they are represented the different bridging technologies, such as power to gas, traditional cogeneration, distributed or concentrated cogenerators, and then localized power to heat, so heat pumps and electric heater directly installed in buildings in order to leverage the possibility of storing energy inside the buildings, and also the concentrated heat pumps installed in the district heating premises that can be acted as again as a user of electricity, excess of energy. In the first part of our activity, we have studied, first of all, several kinds of sector coupling scenarios, and we have picked up the major ones. And here you have some example. The power to gas deployment for system control, which can permit seasonal energy storage and also the reduction of curtailment of renewables. the virtual energy storage for conversion management by means of electricity demand shifting. Virtual energy storage is what I said before, the use of heat pumps in order to shift the peaks, peak load, so you can have a peak load management and also a demand modulation. And this can permit an increase of flexibility of the system. And similar to that, but is centralized heat pumps that directly inject heat inside the district heating piping. The main stakeholders, the main subjects that can use this tool, we think that could be distribution system operators for the evaluation of a solution based on sector coupling, aggregators or energy service company for the evaluation of their portfolio composition and optimization of this portfolio, asset owner in order to understand the financial impact of some technology or the payback of the different technologies that they want to install, and finally policymakers in order to formulate new policy, new regulations and new incentives in order to make faster the penetration of the different technology. So now let's go to speak a little bit about the architecture of the decision support system. We have first of all started working on the framework of SGAM mapping, so the smart grid architecture model. We have defined the domain of our system that we wanted to study, the different zone, the process field, the station, operation, etc. And also we have defined the communication layer, the different protocols. We would like to, by the end of our activity, also make some new proposal for some protocols. And also the information layer, so data management and the data model, and also the functional layer, the business layer, so the use cases and the business models, as I said before. And here there is a picture showing the mapping of the Planet DSS component on the smart grid architecture model. Then we have studied the data model. We had identified the key information that has to be exchanged between the different objects of our system. And we have defined the Planet information model by means of a construction of classes, subclasses, association, and all the information that has to be exchanged inside our system. Here, in this picture, I present you the architecture of the Planet system. The Planet system is composed of four main functional constituents. The first one is the orchestration cockpit, which is the component that can permit the user interface between the person that is using the system and the variable object inside the system itself. So by means of this part, you can define the scenario, we can instantiate the different components and different items of the system. Then there is the coordination engine, which receives the request for ancillary services, for example, and is responsible for the organization and for the controlling of the different components. Then there are the different modules, such as power to gas, power to heat, as I said before, virtual energy storage, but also the electricity supply module, which permit to have the time series of the wind turbine production or the photovoltaic production, and also the uncontrollable heat and electricity demand. And finally, there is a part of the system which is the real-time simulator, the EMEGA-SIM dynamic grid simulation environment, which permit a very detailed simulation of the grid. The user interface can be summarized in this way. We have three major steps. First of all, the user registration, obviously, and then the scenario creation by means of the input of the different time series, the assets, the economic and financial parameters, and all the other input parameters that are necessary in order to simulate the system. Then there is the simulation part and the scenario visualization, the results of the scenario visualization. And in particular, we can have all the different time series, but also some other parameters, such as levelized cost of electricity, CO2 emissions, payback of different kind of system, etc. And finally, you can compare different scenarios together and pick up the best one. Here there are some examples of the use of our tool. This is the part regarding the simulation scenario configuration. This one is the part regarding the unit registration, and where you can input the different technologies, and also you can input the parameters of the technologies, efficiency, nominal power, etc. Then there is also the possibility to input all the cost parameters of the different technologies, the CAPEX, OPEX, or other parameters that are necessary to obtain the final results. And finally, you can have the results, so the time series, for example, of electricity, and then the output parameters. So now we can go to I can go to show you an example of an application of the first version of our tool. We have, for this example, we have used some real data coming from the city of Turin as far as the electric and heat demand is concerned. You have here the load duration curves of electricity, of district heating demand and local heating demand. And then there are also some parameters that we have used in order to simulate the system, such as the installed capacity of wind turbine and photovoltaic systems, and then the mix of the different technologies that are connected to the system. Then we have calculated the levelized cost of electricity and CO2 emission, for example, in this case, using economic and financial parameters in order to calculate, as I said before, the levelized cost of electricity. We need obviously the CAPEX, OPEX, and lifetime of the different technologies. And here you have some results. First of all, on the left, there is a picture showing the power profile and share per user technology during 2 weeks in April. We have simulated 1 year long period of time. And as you can see, the green line is the renewables producibility. The blue line is the electric demand. And the difference between the two is the surplus. And we have managed this surplus, we have dispatched this surplus to power to gas, power to heat, and electric batteries. And finally, the black area is the part that has to be curtailed. On the right, there is the influence of the photovoltaic installed power on renewable producibility, which is obviously linear, and is dispatched to the demand, to power to heat, power to gas, and etc. As you can see, when we increase the installed power of photovoltaic, obviously there is also an increase of mismatch between the electricity demand profile and the renewables production profile, increasing the need of curtailment. In this slide, I can show you the results on the levelized cost of electricity and CO2 emissions, which are the blue line on the left, the levelized cost of electricity, on the right, the reduction of CO2 emissions with the increase of the photovoltaic installed power. In this slide, we can see, let's say, the same results, so the levelized cost of electricity and CO2 emission, but as a function of installed power of electric batteries, power to gas and power to heat. And we have used for the unitary cost of these technologies the forecasts for 2030. And as we can see, even for 2030, it seems that electric batteries are still very costly. And so there is when you increase the electric batteries power installed power, you have an increase of levelized cost of electricity. Instead, on the other hand, the power to heat seems to be a very interesting technology in order to increase the flexibility of the system. And also, as you can see, you have a reduction of the levelized cost of electricity. So I can conclude my presentation saying that we would like that this Planet tool can provide a useful decision support system tool in order to optimize the energy exchange and the synergies between energy networks. This tool is devoted to technical and economical analysis. And finally, we hope that the people that in future will use this tool could be the DSO for grid planning and operational management, plant owner, and policymakers for new regulation and recommendation, and also the possibility of giving new incentives in order to increase these possibilities on the flexibility of the energy system. So I have concluded my presentation.
Thank you very much. Do we have some questions from the audience to start off with? Do we have any questions? Then I will ask you a couple of questions. What do you think so far, in your experience, is some of the most critical success factors to come to success with this? You know, what's the challenges, both to move closer into a more flexible environment, making use of this tool in reality? What do you think is the most important?
Yeah, there are several problems and issues that has to be tackled. I think that the first one is the regulation that is very important in order to make this new possibility of flexibility working well. And so the policymakers and authorities has to work very hard in order to find out a way to make the different parts of the system working together and exchange data. And this is probably for the digitalization, the IoT thing, and exchanging information in the big picture is necessary because there is a problem, obviously, of protocols of communication, but also we had the opportunity to have a workshop in March of this year with different authorities, people, and the problem that they say that is still on the floor, on the table, is that they don't talk together. The people that work on natural gas network don't talk to the other ones. the electricity grid, for example. And so this is obviously a problem.
So
And
to understand it right, in a nutshell, in order to get to flexibility, we need to look at all different possibilities of these ecosystems.
Yeah.
Market coupling, storage, all this needs to fit together.
Yeah.
But from a regulator point of view, they are still working from their different perspectives.
Yeah, exactly.
They are sort of they are only thinking from their perspective, and they are not thinking ecosystem yet.
Yeah.
And then you can take this into how they make policy, but you can also take it all the way down to how they set standards and protocols together.
Yeah.
How do you fix that? Where do we go? How do we help each other out? Is this a European?
I don't know. This is the problem.
I asked a question like this. Do you think this is a European problem or is it a national problem? Is it a TSO, DSO level problem?
I think that is a European problem in general, but obviously each country has to decide probably in different ways. There are different perspectives, different behaviors of the different parts of the, let's say, the policymakers, the authorities, and the people working hard on the field, such as the energy service company or aggregators or let's say all the people working on this very, very complex ecosystem. And up to now, probably there was not the opportunity and the necessity to work together. But now also with the digitalization, with the IoT perspective that, and the data analytics, it is necessary that we find out a way to work together and make things working together in an optimal way, because this is the solution, the optimal way of using the technology that are already
there. We can do this if you let us do it. I have some key questions. This looks very promising, fantastic results. It's still as a research project so far. So if I work for a DSO in Europe, maybe in Sweden, how do I get involved? How do I get, even if it's in research phase now, how can we contribute or how can we learn already now? How can we work with Planet?
We are open to every people that want to give us some advice, because we want that this tool can be in future, let's say in 1 or 2 years, 1 year will be the end of the project, but let's say in 2 years can be exploited So we are open to the cooperation with DSO or other people that want to work with us with this focus and with this perspective.
From my own experience working with this Swedish TSO, of course this is a problem and a project they are working on, but it seems like we are doing fantastic stuff in different parts of Europe, and there is so much knowledge here. So this is what I'm highlighting, that Vattenfall, big corporations that needs to look at this and are looking at this, that they should be working together. They should find the way. So DSOs, they're welcome to take part of the research. So it's a two-year research program still running.
No, we have 1 more year.
1 more year.
The end of the October 2020.
And then
will be the end of the activity.
And then next step, commercialization, exploitation.
The exploitation. I think that we will need
2-3 years.
Yeah, let's say 2 or 3 years. But I think that by the end of the project, we will have already a tool that it will be working. Obviously, we have to tune it to optimize it. But in any case, I think I'm
so it's a good
pretty
timing
sure
to
that
get
we
involved.
will have a good tool in order to be exchanged to people that want to use it.
Okay. Thank you very much. Any more questions or no? Otherwise, thank you very much. Very interesting.
Thank you.